Now, sadly, to actually work this out takes some pretty advanced geometry and even some calculus. So, for this class, here's what I usually say. Let me just give you the result, and I promise to work it out for you next semester when you take Physics 121. The prerequisite for Physics 121 is calculus. So, when I usually teach 121, I'm not teaching 121 next semester. Doug does. Dr. Folsom does. My apologies. So, he will work it out for you. But it's in chapter 4 of the book, and when we work it out, it comes out to be this. It's the speed squared over the radius. And so in my diagram, I didn't put a little r for radius. Let me do that now. But as it goes around, that would be the equation. Let me show you that it works right. Let's just take this ball again that I was spinning around, and I better not spin it too quickly until I fix this string here. But as I spin it around, let's just say it is moving at a speed of 5 meters per second. I'll just make a number. And it feels like it probably has a mass of 100 grams. So let's put that into here. So at 5 meters per second squared, and, I'm sorry, I said the mass, which I want later on. How long is this string? How about I call that 80 centimeters? All right. And so calling that 80 centimeters, and I'll put 80 centimeters at first. But this will be a good chance to show you a little more advanced calculation and to be careful with your units. Because watch this square one, and let me remind you of your math class. I'll come over here, because what I've been trying to portray to you since the first chapter was when you start working with units, treat the units with the same mathematics you would do with your numbers. And so if I had put x, y over z raised to a power of a, how would you simplify that? Well, this would be x to the a, this would be y to the a, and this would be z to the a. So let me do that here. Let me take the 2 onto the 5, but let me also take the 2 and put it for the meters, and let me also take the 2 and put it on there for the seconds. Downstairs, why don't I leave the 80 alone for a moment, but then notice the units here that I have a meter, and it would be nice to have that matching down here. So I'm going to use, back in chapter 1, what does the centa mean? And I'll just remind you, remember, it does not mean cm for centimeter. It means c for centa, that's a number, 100, and then meters. And so I'll just replace the c with the number that it means, and that way I'll get meters. You see, this will come out to be a 25 on the top, and this will come out to be a 0.8, so that'll be my numbers. And this will come out to be meters squared, and then the second squared with the meters. To do the numbers, I'm going to have to grab my calculator here. So if I go 25 divided by 0.8, I get 31.25. And then the units would be a meter cancels with a meter, so I get meter per second squared. And now I can do my unit analysis, right? Look what the units came out. After all this math, the units came out into be meters per second squared. And what should they be? What am I asking for? Well, the question is asking for what is the acceleration? And I know acceleration should come out to be meters per second squared. Is that what I got? Yes, I did. So that makes me feel like I did my logic right. I did my math right. And as I said, this is the equation, even though I didn't derive it for you, and even though it will get derived for you in Physics 121. So this then is that acceleration, and the units work out perfectly. Now, if I continue this and say, well then, what would be the force on this ball as it is going around? Well, that's just from the last chapter here, chapter 3, where what we did is we said if you have the mass, you have the, if you have the mass and the acceleration, just multiply them together and you'll get your net force. Now, of course, net force isn't necessarily the force from the string, unless that's the only force. And so as I spin around, I'm ignoring gravity here, and so I'd say, yes, that's the only force. So if I put in the mass, which is about 100 grams, as I said, and I put it times the acceleration, which we've just calculated to be this. And before I do the numbers, if I remind myself, now wait a minute, what is a Newton? And I don't think we have it on the board right now, but I'll just remind ourselves that a Newton is a kilogram times a meter per second squared. I gave it in grams, so we got to go back to chapter 1 and be careful with our unit here. So I want to convert this into a kilogram. So maybe the way to do this, watch this little trick. There's my gram. There's my 31.25 meters per second squared. If I just put something that has the same in the top and the bottom, that doesn't change anything. So why don't I put a K in the top and the same thing in the bottom? Remember what a K stands for? Right? A K stands for 1,000. So I can take the 100 and divide by 1,000 and get 0.1, and then leave the K with the G, and so there's how you convert the units. That's why I'm saying this. What's really nice about remembering that kilogram, kg does not stand for kilogram. It's K for 1,000, a kilo, and then G for grams. Well, I better wrap it up because this is getting to the end. So let's finish this here, and then we'll call it a wrap for today. There's one little diagram I want to show before we leave here. But let me grab my I guess I don't need a calculator for this. 1/10 times here would then be 3.125. And then there's the kilogram times the meter per second squared, which we say would be a Newton. And so it does come out to be newtons. And so I'm happy that my units do match, so that's my unit analysis. And I switch to kilograms. So now, again, never forget what we did in chapter 1 and how to switch. But there, this is the net force. Am I done? Well, let me say again, net force doesn't always equal the force you're looking for, unless that is the only force. So in this case, unlike the bear problem I did, I would say I'm done. This net force is the force of the string. And so this is what we call the centripetal force, because it is then equal to the mass times the centripetal acceleration. Okay? And so that's our objects moving in a circle. And that's really the first half of this chapter, but I want to show you one diagram, and then we'll call it a wrap for today. And we'll continue on with the second half of this chapter, which is projectile motion. Actually, it's more than half the chapter, so I would say we're probably 40% done with the chapter. The two things, the projectile motion is a little bit longer. But what I hope you got out of these last two chapters, among many things, is if I have an object, and I'll just represent it with a baseball, and that object is moving along in some direction, and in my diagram I'll just say it's moving to the right, then if you apply a force, which means it has an acceleration, in the direction that it's moving, it will go faster. And that's a picture I already gave you in the last chapter. Also on this picture was this, that what if you applied a force, which means it would have an acceleration opposite to the direction it's moving. That would make it go slower. This was kind of my thing about a car. Where is the accelerator on the car? This would be the gas pedal. This would be the brake pedal. Both of them make them accelerate. One makes them go faster, one makes them go slower, but either one is a change. But added to this diagram is what we just did now. And that is, how do you make it turn? What direction do you have to apply the force to make it turn? And so if I were to apply a force perpendicular to the direction it is moving, then it would turn. It wouldn't go faster or slower. It would just turn. And so I will put in this diagram that part. And that's what I've been trying to show you with this string. That if you put a string on the end of the ball and you turn it, it is giving it a force. It is making it accelerating. And it is actually perpendicular to the direction it is moving. And one last thing. I'll change colors here. Maybe I'll even do two sets of colors. If we put this together, what if the car was getting on the freeway, so as it goes on the clover leaf, it's not only turning, but it's going faster? What direction would the force and acceleration, since force and acceleration are in the same direction, what direction would be the force on this baseball for it to both turn and go faster, like a car getting on the freeway? This is where our two-dimensional, our arrowheads come really helpful. Because in order to turn, you need a force this way. In order to go faster, you need a force that way. To do both at the same time, you would need both of those. How do you get both of those? If we had a force that was like this, we could think of that force as made up of some of it in the x direction. That's the part that makes it go faster. And then some of it in the y direction. That's why this is called motion in space. That part would make it turn. And so a force that is at an angle then would be made out of both of those. And so the two together, one are part of the force in the direction it's moving, and part of the force perpendicular makes it turn and go faster. And so I'm going to put down here, if this is your force, which is the direction of the acceleration, this would go faster and it would turn. And hopefully by extension of this, what if the car was getting off the freeway? And so as it goes around the clover leaf, it's turning and slowing. What direction would the force have to be to turn and to slow? Well, this would be the answer. Because you can think of this little arrowhead as part of it going this direction. That's the part that makes it go slower. And then this part. Sort of like I did at the beginning of this tape, where I took that scale and I was pulling with 13. I can think of that as 5 up and 12 over. And so that one force is really made of those two. And that's what I'm trying to say here. This one force, which is down at an angle, can be thought of as this and this at the same time. This part of it slows it down, this part of it turns it. And so finishing up here, I will say this makes it go slower and turn. And so keep that diagram in mind. It's very useful as we talk about motion in space. We can then talk about things that not only go faster or slower, but also turn and also do that at the same time. All right, well, we're way over time, so we'll call that a wrap. And when we come back on next Tuesday, we'll continue on in the second half here of Chapter 4.